Welcome to a Rice University podcast. For more information about us, please visit our website at www.rice.edu.
Good evening. Welcome to this evening's version of the Rice University President's Lecture Series. We're always pleased to welcome so many of you, students, faculty, staff, people from the community in Houston. The President's Lecture Series brings some of the world's greatest thinkers, innovators, and leaders here to Rice to share their perspectives, both with our own community and the wider Houston community. Thank you very much for being here. Our lecturer this evening is a theoretical neurobiologist and affiliate professor of psychiatry and behavioral sciences at the University of Washington in Seattle. William H. Calvin studies ape-to-human evolution, as opposed to the reverse, apparently, climate change, and civilization's vulnerabilities to abrupt shocks. Dr. Calvin began his education studying physics at Northwestern University and then branched out into neurophysiology through studies at MIT, Harvard Medical School, and the University of Washington, where he received his doctorate in physiology and biophysics in 1966. He's the author of a dozen books, most for general readers, about the brain and evolution. His book, A Brain for All Seasons, Human Evolution and Abrupt Climate Change, won the 2002 Phi Beta Kappa Award in Science and the 2006 Walter P. Kistler Book Award. The Kistler Award is given annually to authors of science-based books that significantly increase the public's knowledge of subjects that will shape the future of our species. His next book, Global Fever: How to Treat Climate Change, will be released in February of next year. One journalist described Dr. Calvin as a soft-spoken man whose tone sharply contrasts with the impact of his thoughts. Tonight, we'll certainly see why. Dr. Calvin will address the issue of global warming and how humans are responding to this potential crisis and engaging in the search for solutions. He will praise the conventional methods we are considering to reverse the trend of excess carbon dioxide in the atmosphere and discuss the role of conservation, reduced emissions, and clean energy resources. He then will examine the steps he believes we need to take next. Please join me in welcoming to Rice University and to Houston, Dr. William H. Calvin.
You may have wondered about the pictures. When I started about 3 years ago writing a book on global warming, I decided I needed a parallel project to keep myself cheerful. And so I undertook a portrait study of our closest relatives. So what you've been seeing are mostly bonobos and orangutans and such. Climate change is a big part of human evolution back, say, 2.5 million years ago to present, because climate change is the way that change occurs rapidly in evolution. There's a great deal of stasis in evolution where you stay in the same place for 10 million years. But climate change comes along and a batch of new species get spawned off of the standards and all sorts of new things begin happening. And so as I began looking at how the organization of higher intellectual function in the brain might have been added on to an ape brain, and particularly the issues of enlargement of the brain, which I assumed had something to do with it, but that may not be the case, it was natural to take a look at the climate changes that the people that drill ice cores in Greenland were discovering. And what they were discovering is superimposed on the more stately rhythms of the Ice Age. You had, in addition, a whole lot of glitches that were very fast. And at first, they thought the glitches were experimental errors that say that just as in geology, you can have a melt-off come along and sort of sand off the surface, then you add more on top of that. And sure, there's a discontinuity, but it's because the core was interrupted. And so when these glitches were first seen, it was natural to drill another core someplace else and see if they were there too, and they were. And now what we know is that they occurred during our last ice age, which is what I show here, every several thousand years. They're very rapid. In other words, you make the transition between a cool, dry, windy, dusty kind of ice age climate. You pop up into a warm and wet climate in about 5 years. But you also crash back down again. Not quite as fast, but may take several steps. So these big swings that you're seeing here that have the numbers on top of them represent what our ancestors were living through at the time that they became behaviorally modern, which means that you see anatomically modern Homo sapiens at 200,000 years, which is way off the screen here. But you don't see evidence in the archaeological record that they thought like us until about 50,000 years ago. So it's that arrow that says behaviorally modern, and it's also the time of the spread out of Africa into the rest of the world. You see agriculture over there on the right in the period where our climate stayed warm and wet for 10,000 years or more now. So climate has been a big part of our evolution of intelligence. And as I began to realize, looking at global warming, we were sort of coming up on a great use it or lose it intelligence test. That is to say, unless we use our collective intelligence very effectively for action, we run a considerable risk of plunging most of the societies around the world into tailspins. So I will try to show you the urgency of the situation in this talk. As Yogi Berra once said, the future ain't what it used to be. And I'm afraid that will become a lament of the songwriters of the next generation. But you'll see what happened there. Mount Rainier just turned dark. And if we go backwards, that's what it looks like. All the glacial ice like this on all the volcanoes of the world and other ice that's on mountains rather than Antarctica or something, are projected to be gone probably by the middle of the century. So are all the coral reefs of the world by 2100. That's even if we start doing something about the problem. So what I'm going to do to paint the picture for you is I'm going to spend the first part of it just giving you a history. I'm not going to tell you much about greenhouse gases or anything. I'm going to show you the things that determine the thermostat setting for the Earth and how humans regularly have changed it. And then I'll talk about the more familiar, perhaps to you, CO2, methane problems and how you substitute for the fossil fuels to take away some of the adding to the problem will go on. And then I'm going to talk about a section called the tortoise and the hare, which is all about how quickly we must act. So how bright is the Earth? Well, it's called albedo in technical terms, but it basically means how much of the sunlight does the Earth reflect right back out in space before it can heat up anything. This occurs from clouds. The average amount of clouds on the Earth, if it changed a few percent, could do the same thing that all the greenhouse gases have been doing. And we have no idea what controls the average amount of clouds on Earth. The other thing, of course, is there's ice and there are deserts that reflect a lot. Here, for example, is a rock from space. You see the Tigris and Euphrates rivers coming down into this very bright desert, and then it gets dark. All the dark there are leaves. It's agriculture making use of the irrigation that is achievable from those rivers, and this, of course, is one of the singular events back in the beginning of agriculture about 9,000 years ago. So agriculture may darken what's otherwise light-colored land and absorb more heat and warm the world. You can also see something the opposite. Here from space is a picture, a national border that you can actually see from space. It's the border between Egypt and Israel in the Sinai. So that's the Mediterranean up there on the upper corner. There's about 6% ground cover on the Egyptian side and about 13% on the Israeli side. And you might ask why this is so and why has it persisted for 40 years and why there aren't exceptions. And basically what you see on the Israeli side is the starts of vegetation taking hold. You see these clumps of plants. Their root structures are interdigitating and sort of holding everything in place. And you don't see as many of those on the Egyptian side. And the difference is because the Israelis have treated this as a nature preserve. They've not allowed grazing animals there. The goats on the Egyptian side tend to break up these root clusters that are forming with their sharp hooves as they're eating. And that simply means that next time a big wind comes along, a lot more sand gets up and moves, and you wind up with the active dune kind of situation you see. So that sand that gets mobilized buries a lot of the starter soils. So this is a case, again, of albedo change, but in fact, reflecting more back because the goats did it. Now here's a familiar example. That's a leaf laying in the snow, and you see how much the snow is indented under it. The leaf is darker, it absorbs more energy. The snow surface is reflecting, and fresh snow reflects about 90% of the light back into space. Put a dark object on it and it heats up and melts what's underneath and it sinks. That's why the sunken leaf. You get a similar effect if you blow dust or something on top of the snow or ice. It serves to heat it up nicely in the sun, and you get much faster melts. The picture here is the Rockies in Colorado with dust blown in from Utah. But you get a similar effect from wildfires that produce a lot of soot that falls out. This is one of the reasons, perhaps, why the Arctic floating ice has been shrinking so badly, much faster than any of the models showed, and the models didn't include things like soot blowing in. So that's not a settled issue yet, but I'm trying to show you here, these are all things that affect, in essence, the thermostat setting of how warm the Earth normally is. This is looking down on the North Pole, which would be under the letter E in winter. And what you see on the left is, here's Canada and the US over here. Here's Siberia wrapping around to Europe. Here's Iceland down here. Now, this is Greenland, but all this stuff above here is floating pack ice. Snow falls there and piles up, but it causes the ice to sink, and the bottom of the ice actually just goes back into solution as water. So it never gets more than about 3 meters thick. If you dug a basement up there, you'd have a swimming pool. Now, Greenland, on the other hand, is a nice solid rock foundation, and that's what it requires to build up a big thickness of ice. In Greenland, it's about 2 miles deep. But what I want to show you here is all this green around the edge. The satellite measurement is looking for chlorophyll. And it's comparing over time, this is 1981 through recently, and the light green areas are regions that have been getting more and more chlorophyll over the years. And this is mostly not trees growing, this is just ground cover. But as you can see from what I said before, that's sure to absorb a lot more heat and generally cause more things to melt even faster. So this is one of the feedbacks in the system that's working against us. One of the others is soot from fires. This is a monthly movie here of the number of agricultural fires that you can see from space. Each dot represents at least one fire within a 10-day period. So you see this enormous wave in Africa, for example, between the Sahel now and then shifting down into the southern regions for agriculture. You can see it's spreading across the U.S., starting in the south and spreading up through the northwest after another month. This is a background of fire, which is far, far in excess of wildfires, which have always existed and have periodically, burned down forests, which then have to regrow. This is an annual, around the year, addition to the Earth's atmosphere of a fair amount of black carbon. And the black carbon gets heated up by the sunlight. It re-radiates in the infrared energy to the surrounding air, warms it up. Okay, now I'm going to talk about 50 years worth of what's been going on with climate. This is a satellite picture of what the Pacific looks like in terms of temperature. And the orangish waters are where the surface temperature is above about 80 degrees Fahrenheit. That's a critical temperature because any water that's cooler than that won't support a hurricane. So these are hurricane-ready waters. This is a picture of 3 hurricanes, or typhoons, as they would be called in Asia, at the same time. This is not a composite picture. This is one day in August last year. 3 at once. So I'm going to go through here some of the causes for a lot more high winds and such. The projections for more high winds, and the evidence is we've had more high winds, because when warming is going on, the land warms up more than the ocean does. The reason is pretty simple. There's evaporative cooling in the ocean, and on land, evaporative cooling sometimes runs out. Say hot and dry rather go together. When you had a big drought here last year, you were also a lot hotter. We've seen heat waves in Europe that killed 5,000 people 4 years ago. And I'm going to go through floods and droughts and wildfires now. Here's an example of high winds. There were 20 big trucks like that blown over one night up on the Utah-Idaho border. 113 mile an hour wind gusts. Same year in Seattle, this is what happened. This, in fact, is over near Bill Gates' house, and that is a garbage truck that blew over on a rather nice Mercedes convertible. Now, if you ask the insurance companies about high winds, you get a surprise. This is what's called nonlinearity in the world. You would think if the wind speed, the peak wind gust, went from 50 miles an hour up to 60, that's a 20% increase, that maybe the damages go up 20%. The answer is they go up 500%, just with that little 20% increment. In other words, the insurance claims are now 6 times what they are for 50 mile an hour wind. And this is not a prediction, this is just the insurance company's experience. We've been seeing a lot more floods, and we tend to think these are, when we don't have them, someone else is having them, and so forth, and it might average out. But one of the strengths of the IPCC reports have been that they've collected the worldwide statistics on all this with the following results. This is a graph of floods in the Americas. This is the number of major floods in the 50s, in the 60s, 70s, 80s, 90s. And you can see an enormous increase in the Americas for major floods. And the same thing is true on all the other continents. So we have been living with pretty major climate change already for about 50 years. This is the drought map for the US a year ago. As you see, Texas has a major drought then. If you look over into the deep south, there's not much drought there at all. You look over in Southern California, there's only the beginnings. And this year, in fact, you had record rainfall. This is what's meant by more extreme weather, okay? Even if you find a place in Europe, for example, the prediction is more rainfall at the higher latitudes, less near the Mediterranean. Even if you found a place in between where it didn't change, there would still be greater extremes at that site, and it's the extremes that do the damage. So here's the current drought map, or at least this is a series that will walk you through the last 6 weeks. And this shows you the trouble, for example, that the Deep South has gotten into in just 1 year. And similarly, you see over in Southern California, same kind of big problem. Now, I've marked 32 degrees north on these for a reason. The same story recurs at 32 degrees in other parts of the world. So this graph shows you the percent of the land surface around the world, the 30% of the surface that's land, the percentage of it that's in drought. And back in the 70s, it was about 15%. During the 1980s, it took a jump up to 25% and stayed there, with excursions to 35%. Okay, so this is a real climate shift that has happened to the Earth. The best guess is this represents an expansion of the tropics, though the issue really isn't settled yet. But basically, all the areas that have Mediterranean climates around the world are having the same problem. Some years it goes away temporarily, but a lot of it has been a chronic problem for decades. A Mediterranean climate is where the rain falls in the winter, but it doesn't fall in the summer. And of course, it's ideal for growing grain crops and things like that that could get bowled over and left to rot if you had a rainfall at the wrong time of year. So obviously the Mediterranean is a Mediterranean climate, but so is Southern California. So is South Africa, the Western Cape region, and over in Australia, the area around Perth is also. This is where the westerly winds finally develop, and the areas towards the equator from all these regions is desert. So basically, a Mediterranean area has a desert climate during the summer, but during the winter, the low-pressure systems sneak in and provide rain. So it sort of looks like what's happening is the low-pressure systems aren't sneaking in the winter anymore. You get a lot of fire danger in the Mediterranean, had quite a lot of trouble. This is Perth, Australia, back in that corner, and this is just a satellite picture of the chlorophyll and such, showing you the areas that are really parched versus the green areas that still hold water in the dry season. But the important information is down at the bottom. Perth has a record of the river inflows to its reservoirs, and they go along until about 1975, and then they drop by half and stay down. In 1997, it took a second drop down to 1/3, and it stayed there. So, this is not, you don't say that the Sahara is in drought, you say it has a dry climate. This is a climate shift into a dry climate. This is what happened a month ago in Southern California. All those little red dots are fires, seen from space, marked the same way as before. This is the aftermath of the fires, and this is a false color representation where the red areas, like this one, are regions that have burned this year. There's some earlier fires shown here that don't show red. So this is the last half year's burns. And there's an awful lot of red as you get down to San Diego. So really substantial areas have been burning off here. And again, 32 degrees is the Mexican border. Okay, this isn't the previous graph. This is one about wildfires rather than floods. And again, you see that major wildfires by decade have been soaring in the Americas, and in Europe, and in Asia, and in Africa, and Australia. So that's what's been going on, and the IPCC reports have pulled these together. This is quite independent of their projections about what's coming in the future. This shows you what's been happening to us without us realizing how widespread and bad it is. As you might expect, this is just a graph of the red bars are just the number of wildfires each year from 1970, and this is just the western U.S. forests. But the black line is the temperature that year, and as you see, there's a nice correlation. Say years that are hotter also become dry out the forests, and they catch fire more readily, and with stronger winds, you spread them a lot further. All right, now let's discuss getting into hot water, by which I mean ocean surface temperature. This is the oceans of the world. The 6 major ocean basins are the individual lines, and the average is just that black line. And what you see is they've been warming steadily since the 70s. So if anybody tells you it's a heat island effect, tell them that that hypothesis was abandoned about 40 years ago. You see this one interesting dip in the middle. That is due to this. Mount Pinatubo in the Philippines blew its top and injected a lot of material up into the upper atmosphere, into the stratosphere, where there's not much weather. That's where, jet planes like to cruise in. Now, what this does, the sulfates in it tend to attract water, and they just get a lot of water around surrounding them, but that's shiny. And shiny creates an ability to reflect sunlight back out into space. So that's the basic explanation given for how you get this 2-year hiatus in warming here. This has led to the proposal that maybe we should just inject sulfate into the stratosphere ourselves. If you don't inject it into the lower atmosphere, you don't get acid rain. If you inject it in the upper atmosphere, it hangs around for 2 years rather than 2 months, or 2 weeks is about all it lasts in the lower atmosphere. So that's one of the things that are suggested for dealing with heat waves, but it doesn't do anything about the basic problem, because the CO2 has a second effect besides creating an insulating blanket around the globe. That is ocean pH. The oceans have absorbed about half of the excess CO2 that we have created in the atmosphere by burning coal and oil and natural gas. Reducing the pH makes the ocean more corrosive of the shells of animals. The projection is, it's already fallen in the 20th century by about 1/10 of a pH unit. And the suggestion is there's another 2 or 3/10 in other models for what's in store for us. Now, laboratory studies can be done with controlled pH seawater to show you what the effects will be. And basically, the shell-forming plankton, the coccolithophores and so forth that have little, I think I have a picture. No? I guess I took that out. Form calcium carbonate shells, limestone, in other words. And when they die, they fall down. And that's a major way of taking carbon out of circulation instead of putting it into circulation. And the ocean acidification will start interfering with that. It will also dissolve coral reefs. That is, say, as you lower the pH, what happens is the coral reefs, calcium carbonate, starts going back into solution in the seawater. So it's just like a cube of sugar in the bottom of the iced tea. It starts crumbling, and so that's one of the reasons the coral reefs are in trouble. But there's another reason, and that's literally hot water. To remind you of 2 years ago when the pathways into the Gulf of Mexico were particularly warm. And what warm water does is to distress coral. Coral is a combination of an animal, the coral itself, and a symbiotic algae, the scum on your aquarium, basically lines these coral appendages here. And the white one represents a coral which has ejected all of its algae because it was distressed. I mean, it will do this for other reasons, like sunlight that's too bright because they're too close to the surface. It's a distress reaction of the coral. But if the temperature or sunlight doesn't go back down in a couple of weeks, the coral dies. So it's well known from laboratory studies just how many days of excess temperature it takes to do this. This is what's happened to the Caribbean in 2005 in the summer heat wave. The little orange squares are the temperature measured by satellite during the nighttime, and the boxes are only where the number of degree days was sufficient to kill coral. So that's an enormous area, both in Central America and further out into the islands, where you go and look. Sure enough, in the Virgin Islands National Park, for example, the divers reported coral reefs even 70 meters down were killed. Okay, this is the whole world temperature warming in just the last 5 years, compared to the temperature at the same place, about 25, 35 years ago. So 1 to 2 degree Celsius warming, the red colors are the 1 to 2 degree range, and that's 3 degrees Fahrenheit. Okay, so a lot of high latitude in the north regions and some in the south, as you see, have warmed up quite a bit. And they have predictable effects on the pack ice that melts during the summer. So this is the end of summer. This is, again, looking down the North Pole where the dot is. And that's the boundary of the ice at the end of summer. It's the middle of September, before it starts growing again. That's this year. And if you can see the little green line in between the two, that's 2 years ago. So major things are going on. Now, there's no sea level rise from this because it's already floating ice. But next door in Greenland down to the bottom, it's not floating ice, it's 2 miles high piled on land. All the way around the edges of Greenland, the summer temperature gets up above freezing, and so the surface starts melting, and it certainly changes its albedo and stops reflecting as much sunlight back and absorbs 2 or 3 times as much. But the real way that Greenland loses ice is not by runoff, it's by exporting ice to the oceans where they promptly raise sea level even without melting. It's called, icebergs. There's the biggest outlet glacier in Greenland. It's at 69 north on the west side, called Jakobshavn. Let's try water. It advances 30, 40 meters every day in the summer, which is twice as fast as it was doing 10 years ago. This particular one is 5 miles wide, and let's see, 30 to 40 meters, that's about 8 to 10 parallel parking spaces in distance. So that's the daily output that used to be half of that. Well, this gets us into sea level rise. That is out in the middle of the Indian Ocean. That's the Maldives. That's the capital city and only city. 250,000 people live there. But the average elevation is 1.5 meters. Now, just from thermal expansion of the oceans for taking in heat, the sea level rises. The extra put in from Greenland and Antarctica, and the mountain glaciers like Mount Rainier that's losing, all their stored moisture, are just adding to that basic thermal problem. We know from about 125,000 years ago how much the sea level rises when you lose about half of Greenland to warming, because we did lose about half of Greenland to warming 125,000 years ago. It was for a reason other than global warming, but we can extrapolate very easily to what global warming would do to this. Basically, a global warming of only 1.6 degrees Celsius, 3 degrees Fahrenheit, would be sufficient to create this condition again. it resulted in a 6-meter sea level rise, about 20 feet, sort of a 2-story beach house is about the amount. This is what it does to the U.S. coastline for the Gulf and the East Coast. If I zoom in here, show you a more familiar coastline, and I'll zoom in again, show you the local real estate situation. So there's no telling here exactly how fast this will occur. It's generally thought that the sea level rise will lag behind the temperature by perhaps centuries, but in fact it could go faster than that if you had a real collapse in either the West Antarctic or the Greenland ice sheet. So we know in Florida what a 6-meter rise does. Most of the population of Florida lives on that coastline. So this is 15 million climate refugees. That's the East Coast. Down here at the bottom in North Carolina, that incursion is about 100 miles. It doubles the width or more of Chesapeake Bay. It does quite a lot in Philadelphia, New York, and in Boston. A 6-meter rise covers up MIT, but spares part of Harvard. There will be a new Harvard Peninsula extending out into the new Boston Bay that will be Harvard Square. So 1/4 of the U.S. population lives in the Strip. And around the world, quite a lot of the population lives within commuting distance of a coastline. So this is a particular piece of real estate. That's a view of Washington, D.C. And you can see, I mean, my favorite collection of good museums is all along the mall here. If they don't pay sufficient attention, this is what will happen. That is to say, the White House lawn will be waterfront, and the Capitol steps will be where the tides go up and down. It's a lot worse in Asia, because Asia has a whole lot of very productive river deltas that a lot of people live on. So the red here shows you the 6-meter, 5-meter rise. And as you can see up here in Bangladesh, there's major incursions back in there. It basically covers up half of Bangladesh. Bangladesh has 144 million people. So there's 70 million climate refugees right there. And the situation in these other deltas is of similar magnitude. One of the Chinese deltas, 93 million people live there. All right, let's go to the villains here. This is the rise in CO2 since 1958, when they started measuring it, because the oceanographers in the mid-50s, everybody had been discounting the calculations done by Arrhenius in the late 19th century that showed that we would have this kind of global warming if we kept putting fossil fuels in the air. People discounted it because they thought the oceans would take it up. And the oceans have taken half of it up. But back then, they realized the oceans weren't going to take it all up and that it would better get serious. And so they started measuring the CO2 on the top of Mauna Loa in Hawaii to get away from industry. Then we discovered, using the ice cores, a technique for finding out ancient CO2 and methane levels, basically little bubbles in the ice of ancient air. So you take one of these ice cores, you slice it to get a section at 500,000 years ago, you put it in a jar, you evacuate all the air in the jar, and then you heat it up. And the air from the bubbles comes out, you measure their CO2 content, and that's what the plot is here. So in the ice ages, the CO2 goes way down, about 180 parts per million, and then in the warm periods, it comes up to about 280. But basically, it's never got above 300 until now. We passed that point about 1950 or so. So we're way over, we're 100 parts per million over, that previous maximum. So that's what we call excess CO2. And that's what we've basically got to get rid of to restore the climate. This is just a plot again of the same thing at the top. Shows you that the carbon dioxide's gone up 37% in the last 150 years. That's the spread out on the right. And it shows you that methane went up and down about the same time, but it has soared 130%. The bottom shows you the temperature in Antarctica that accompanied all this, and you can see the temperature hasn't gone up anywhere as much yet as you might expect it to from those. Now, one of the virtues, just as the rains will clear out the sulfates within several years from the atmosphere, from the upper atmosphere, methane has a short residence time. It's about 6 years to losing half of it. And so if you go tighten up all the leaks in the natural gas pipelines, like the one from Russia to Great Britain and such, you ought to be able to make an immediate impact. And indeed, the methane concentration has started to dip recently, probably for exactly that reason. But CO2 doesn't go away. The half-life is at least a couple of centuries, and even in 1,000 years, about 25% of it would remain based on what we know. So these are the fossil fuel uses that have gotten us into the mess. I'm breaking it out here just by what they go towards, like producing electricity, that power sector, 24% of the pie. Transport is 14%, buildings, heating them and everything is 8%. Industry at 14 is things like smelting aluminum and building cars and so on. There's this whole sector in the other side of equivalence to CO2. And what that means is methane is 23 times as effective at insulation than CO2. If you take its concentration, multiply by 23, you can sort of add it on to CO2 to get a CO2 equivalent concentration. So let me go through some of the things you can do to change this picture. Let's talk about transport first. Basically, getting commuters off of oil is within sight, I think. This is Honda's car that will go into production next year, and it uses a fuel cell powered by hydrogen. Fuel cells are basically batteries where they produce electricity, but you have to keep pouring in liquid of fuel of some sort, in this case hydrogen. Trouble with hydrogen is you've got to have a filling station for it, so only big fleets like governments and so forth will actually have hydrogen-powered cars. You've all heard about plug-in hybrids, that's to say things like the Prius, but with battery enough to power the daily commute entirely off of the electrical grid that charged it the night before. There's a third possibility for using electricity to make a portable fuel, and that's compressed air. And in India, they're going to produce next year the first 6,000 taxi cabs that will run entirely on compressed air. And this is not a jet coming out of the tailpipe. This is compressed air used to run a piston engine. So instead of exploding the fuel to push the piston down, they inject compressed air. This will be very popular in the tropics because these engines, instead of running hot, they run cold. As you know from the can of compressed air, when you're spraying it on something, it gets very cold. Well, these engines will get very cold, and they'll provide free air conditioning and dehumidification. I mean, furthermore, these are simple enough. They don't require batteries and fuel cells that you'd have to buy abroad. This is something that many countries could produce with their own raw materials. So there are some promising things. Let's talk about power, producing electricity basically, including all the extra power you'll need for the transport sector that you're taking on. This is just the electricity growth in the U.S. since 1971. And the various bands are just the various sources, coal at the bottom, then oil, then gas. So those are the fossil fuel parts of it, which at the present is about 68% of the total, and then nuclear and hydro. Now, this may puzzle you because many of you will know that we have not started a new nuclear reactor since 1978, and yet this is getting fatter and fatter. It's about twice as big now. That is experience. That's people learned how to run them much more efficiently to minimize the downtime, and so they are producing at full capacity. Instead of 44% of the time, they're up into the 80%, and some of them are 97%. So that's a worldwide experience. I mean, the rest of the world didn't stop building nuclear reactors, so this is the world's experience in making this better. So just remember that 68% of our electricity is dirty. Only 32% is clean. In France, 91% is clean. They get only 9% of their electricity from fossil fuels, and it's because they have built all their new capacity basically from nuclear. Next door in Switzerland, the electricity is 99% clean. They get about half from nuclear, half from hydro. Next door in Germany, it's about 32% clean. UK is about 25% clean. China and India are about 20 to 15% clean. You might ask about Texas. 9% clean. National average is 32% clean, but Texas is the biggest consumer of all of this, and it shows up in the per capita use of electricity. This is, since 1960, a chart, the upper one there, of the United States per capita consumption of electricity. So back in 1960, we were using about 4,000 kilowatt hours per person year-round, and it's triple that now. However, you notice the black line there, that's California. In the mid-70s, they started doing something about the problem, and despite all the additional computers that we now use, and Californians used a lot first, they have held per capita consumption down to what it was in the 70s. Texas is twice California. It's well above the national average, about 14.4. It's off the top of the graph here. You might say that's because you all need a lot more air conditioning and a lot more heating in the winter and so on, but New York State is almost as good as California, and they have all those same needs. So I'm presenting this to show you that government policy matters, that different countries, different states have done things differently, and one of our jobs is to learn from that experience. Skip that. Our problem, in order to put the growth into clean energy and not increase the emissions anymore, is that you've got to add a couple of gigawatts capacity. 1 gigawatt is about one nuclear power plant or one big coal plant. So it's sort of my standard unit for no solar array, even the one in the Mojave Desert, is even 1/10 of a gigawatt, averaged around the clock like the others. So there's this need. China is building at least a gigawatt every week. The U.S. plans to build a new gigawatt every month of coal-fired capacity, although things are changing, as you may know, certainly in Texas. But that's just for the new growth. That's not doing a thing about the every year emissions. In other words, when people talk about stabilizing emissions, it's really a misnomer. All it means is adding the same amount every year rather than more the next year. taking the growth out of it is the first target to meet. And it's the one that we've got to do so quickly. I should say that wind and solar, while are big favorites, they don't scale up very well. They're fine added to the grid in small quantities, but they fluctuate. And the only way to avoid blackouts where the grid gets tripped is to perfectly match load and sources so that they're always in balance. And the operators of the plants are very good at this. They look at the weather forecast and they know what time of day people turn on the air conditioners, and they guess quite well. However, if you have elements in the grid like solar, where a cloud goes by and cuts it down, or wind comes up and increases things too much, you can trip grids pretty easily if a fair amount of the power on the grid is coming from those sources. So besides not being large in capacity yet, you're also going to have to redesign the grids using control systems theory that is yet to be developed. This shows you the pie chart for all U.S. energy use. So this has got transportation industry and everything in it, not just electricity. It shows you that 86% of our energy comes from fossil fuels. 8% comes from nuclear, and 6% comes from things that look renewable. That is to say, burning biomass, corn stalks and sawdust and so forth, or ethanol, uses in vehicles, is up about 3% of the total. Hydroelectric is about 3%, except we've maxed out hydro pretty much. And wind and solar are those small quantities up top. So if you want to get a nuclear-sized slice, and we need about 10 of them, to get even one nuclear-sized slice out of solar would be a 133-fold increase in solar. Doing geothermal, which we could do a lot of, we haven't done it anywhere as much as we could, 22-fold increase. So it's kind of hard to do this in a big way, given that we're starting from 86% fossil fuel. The one bright thing on the horizon here is what's called hot rock or deep geothermal. And this is just starting to happen now in France, in Switzerland, and Australia, are all hoping to have commercial quantities of electrical power from this in a year or two. And this is a technique developed with the oil industry for stimulating oil from deep shale and such, where they drill way deep, they do a pressure injection to try to force open cracks in some of the layers down there. And that makes it easier for the oil to flow to the pumps. For deep geothermal, what you do is you open up some of the cracks in granite that is about oven temperature. And granite is flexed and folded and so forth. It's got lots of layers to it. And all you do is open up those layers that are sort of mineralized together. And you then sink a second well down, and you pump water down the first, and it flashes into steam and shoots up the second, and it runs an old-fashioned steam turbine up top that generates electricity. This is exactly what you do in a nuclear power plant and a coal plant and so on. So it's an old-fashioned technology up top. The only thing technical about it is drilling that well. And it currently costs about the cost of a coal-fired plant, to do that, to get a similar quantity of electricity. So it's in the same ballpark, but of course it has no pollution, no runoff, no trucks going into the site all the time. It's a very small footprint. It's just a sort of a parking lot-sized structure out somewhere. It wouldn't even really need a security fence around it. I mean, so this, if you just Google MIT geothermal report, you'll see some of the details of this. But the estimate of the experts last year was that the potential capacity of this is at least 1,000 times the current U.S. electricity use. So this is not a small matter. This is something that we actually could use to, in the long run, to do even better than nuclear And it's a method that, if ramped up in the short run, might solve some of the immediate problems. Now, this is the other part of that pie of fossil fuel uses. These are equivalents to CO2. I told you methane, was an equivalent. You can make equivalents out of a series of other things, like the nitrous oxide, a greenhouse gas that you get from fertilizer. You also, from agriculture, get speeded up decomposition of the organisms in the soil, which then release CO2 to the atmosphere, just by plowing the earth. So the method of agriculture that does a lot of plowing is itself causing global warming. These add up to 14% of the total problem, which is equal to the transportation sector. So there's a lot of potential for improvement in agriculture that would help us address the problem. But the sector down here called land use at 18% shows you another problem. What this means is changes in land use that serve to warm or cool the earth. When you extend the city out into the suburbs and convert land that's light-colored into blacktop that's dark-colored, you're doing a land use change. But the primary land use change is converting forest into agricultural fields. And most countries are doing the opposite, but the biggies are Brazil and Indonesia is 10 times the problem of Brazil, despite all the chopping around the edges of the Amazon rainforest. It's far, far worse in Indonesia. And that total is 18%. So the problem is that reducing emissions is not enough. Reducing emissions only, in effect, delays the agony. All that carbon you continue to put up there stays there for long enough for a civilization not to outlive it. So the only way to basically get rid of what we put up there is to take it out of the atmosphere and put it into long-term storage. Now, sink it to the ocean floor is a method. Plant more trees is a method. There's a batch of candidates here I won't be able to go through, but this is the problem with doing it with trees. That is, say, if you have a global warming forecast that says even more hot, dry, windy conditions, you can bet that fires are going to destroy your project sooner or later. And that it's just simply, there's a lot of good reasons to plant more trees, but security against global warming is not one of them. Well, the oceans already do about half of the photosynthesis. The little microalgae that are aquarium scum and such do about half of the total photosynthesis. They feed the zooplankton and both of these are things that the whales love to consume. Whale feces, which are rich in carbon, sink. And they can sink far enough to be taken out of circulation. That is, it will be 1,000 years before that ever gets back to the surface and back into the air. So that shows you one way, and the shelled animals that die are the other, because they sink. So those are major candidates for doing this, but there are a few others. Let me finish the plankton. You may have heard that one of the critical nutrients, you get these blooms of phytoplankton, and when they exhaust the nutrients in the area, then they stop. And but the critical nutrient for most of the time is iron. And iron usually arrives either by stirring up the bottom that's got a lot of iron on it, which happens in a few places, or mostly it happens because dust from the deserts that are rusty, as you may notice, is carried into the ocean, in this case the Mediterranean, but it happens all over the world on the western coast of continents. So there are some proposals to study this process using iron filings from ships and so forth to get a better handle on it. But that's one of our possibilities. But it may just create more photosynthesis to support more metabolism for the organisms in the ocean itself. I mean, it doesn't necessarily sink more, except insofar as this rain of debris from the surface. Here's Coccolithophores. This is a micro snail. Its wings are modified feet, in effect. Its shell is also calcium carbonate. These are salps. They make heavy fecal pellets rich in carbon. The circles there show you the tail end of their digestive tract that's dense. That's them in the manufacturing line. And salps, which look like jellyfish but aren't, they're really tunicates. One of them would fit in the palm of my hand. They're good size, so they make much bigger fecal pellets than any of the zooplankton, which are teeny. So their feces also have a chance to sink to the point where they're out of circulation. They don't have a chance of getting back into the atmosphere for a very long time. Okay, that's the background of things that we know we could get a handle on some parts of the problem with. We've got a lot of good science, we've got a lot of good technology already for implementing major fixes. We may get a handle on the sinking, taking out circulation problem, and we may learn to bury our biofuels like sawdust and corn cobs in garbage dumps that are sealed. I mean, there's a number of, take solids from treated sewage, for example, very rich, and you can isolate those as well. So there's a variety of things we can do, but the real problem is time. And I want to show you, this is the tortoise and hare fable from Aesop's Fables. And basically it's about the tortoise and the hare race, and of course the hare jumps way ahead in its jerky fashion, and the tortoise plods along, but the hare gets bored and takes a nap. You know, the tortoise passes him and gets there first. Well, there's a lot of aspects of climate that are kind of jerky like that hare, and the aphorism amongst the people that study ancient climate, like Richard Alley, who was here recently, in fact, I think this one's due to him, is climate's like a drunk. If you leave it alone, it will sit there, but once you force it to move, it tends to lurch, stagger. And that's more or less, now, here we go. The IPCC reports, we've had 4 major ones this year, that you've all been reading about in the papers, I suspect, tackle only the slow, steady, tortoise-like part of the problem. That is, say, they make predictions about what will happen if something doesn't interrupt it and set back. And what I want to now cover in closing really is the what's not in the IPCC reports that are causing the governments that commissioned the reports to really underestimate the scope of the situation. In effect, these IPCC scenarios that we rely on so much really assume that the hare is going to take a long nap, and I think that's not a safe assumption. This shows you the Amazon. I'm just going to show you one example of abrupt things that could happen that could set us way, way back. This is the Amazon, and the color coding is green is rainforest that is wet enough not to burn. And we used to think all rainforests must be like this, and until we discovered otherwise. The first big El Nino in 82, 83, we saw a lot of fires in rainforest. And this is the Amazon at the end of this last big El Nino in 97, 98. All the red dots, like before, are agricultural fires mostly, or land clearing fires for converting forest into new lots. The tan color is very flammable forest. The darker brown is just merely flammable in December of 98. So that's the condition at the end of the last big El Nino. big meaning more than about 2 degrees in the Central Pacific, which we've had about 3 episodes of. Here's the graph of Central Pacific temperature, which is the basic El Nino La Nina index. If you get over 1/2 degree from the baseline, you call it an El Nino in one direction and a La Nina in the other, and the shaded areas show you how far they went and how long they lasted. So you see they all lasted no more than a year above the threshold. Now suppose that one lasted twice as long. I mean, mind you, you can see that they have lasted twice as long, like right here, but they weren't also big. So the chances of us getting another big one, given this history, are pretty good. In fact, it's been 10 years since the last one, and the interval between the others is 10 and 15 years. But nobody knows if there's any sort of cycle involved, and we certainly have no way of predicting the duration of one from any of our science yet. But you would sure bet that one of our major risks in this is a El Nino that did last long enough and was big enough to burn down the Borneo and the Amazon rainforest. And some people have done some calculations as to what this would do. Down at the bottom here, I'm just showing you what the progression without an El Nino is. It goes up about 2 parts per million per year, so here's 10 years of progress. Now, if you burn off those rainforests in substantial amounts, the rate at which the CO2 goes up from the fire is instantly, and the rate at which dead wood rots is a bit slower. But basically, you pop up about 40% in that short 5 years, 10 years period of time. So we already have this 100 part per million excess CO2, and this would kick it up another 40. So in terms of symptomatology that we're already getting, we would expect a big jump from this event. It certainly would set back many years of progress that we might make if one of these came along. But it's worse. Without all of those leaves, there's not as much photosynthesis to take CO2 out of the air. And so the rate at which fossil fuels change the air concentration is 50% faster. And as I say, we don't know quite when, but it's in the, I would not call this a fanciful area. This is an area of major risk to us. Even if we can't put a number on it and be terribly exact about the probabilities, this is not something any reasonable insurance executive would ignore in setting the premium for the insurance policy. Well, the big burn also causes a major loss of species. It's a mass extinction event. Ed Wilson estimates that you'd lose about 50% of the species in the Amazon, at least. And it's probably similar in Borneo. So here's 3 of my favorite Amazon species seen recently. And I've got a lot more, but I really have to figure that half of them might be gone. And the same thing, here's Borneo, 2 of my favorite Borneo species, orangutan and saimang. Same problem. So now let me talk about the deed and the ability to turn on a dime. We tend to assume this can't be done, but the IPCC reports show you that it really has to be done. And let me show you the reasoning, because you hear that there's sort of a 10-year window, say 2016. Jim Hansen says 2020 was the figure I was using, but it's soon. And this is the graph that's in Science this week, news article, that shows you just the temperature change above pre-industrial and the time on the axis. So this is progress so far, this increase here, which is about 0.7 degrees Celsius. We're already that far into the scale. 2 degrees is here, 3 degrees. Now, all the things listed on the right about when things will happen at what temperature are predicated on the hare taking a nap. They're what you get if you have the slow, plodding tortoise-like getting worse. So you look up here and you see a big loss of Amazon rainforest up at 2.5 degrees. But I just showed you that this sort of thing could occur at current levels of warming. All it takes is a big El Nino. Well, let's talk about the difference between a 2-degree warming and a 3-degree warming. 2-degree warming is the loss of all mountain glaciers, so Mount Rainier now is missing its ice, and so are all the other ones, and all the coral reefs disappear, although the individual coral species don't necessarily go extinct. A 3-degree warming is so chaotic that there's climate refugees in the hundreds of millions trying to escape wherever they are and go somewhere else. Say Bangladesh. Where are they going to go? Okay, what country will add to its current burden of coping with the same problem? You know, basically, major border crossings like this set off wars, and in this case, they'll probably set off genocides in a great many places. This is not a pretty prospect. This is a major downsizing in the human population in circumstances where, when it's over, all the surviving groups will hate one another for very good reasons. So those are the kinds of risks that we're playing with, and neither 2 degrees or 3 degrees is very nice. But it's what we do in the next 10 years that depends on us limiting it to 2 degrees. And that comes, well, there's another choice, and that is to remove CO2 from the atmosphere. And I've just sketched that in as the sink into long-term storage, the CO2. That's the unmentioned, it's not in any of the scenarios, nobody's talking about it, but it's the only reasonable thing I can think that we can do, is simply to do a reverse on putting carbon into the atmosphere and take it out. So here is the critical curve. Now this is just a modeling exercise that's part of the climate projections. And this is carbon emission that's being plotted, and currently the world is putting out about 8 new gigatons every year of fossil carbon into the atmosphere. So that's where we are. If we continue to grow the uses in what's called the business as usual scenario, which is what was called the pessimistic scenario in that color chart, we will wind up with about a 6-degree warming at the end of the century. So we really have to change our ways, for that. But how fast we have to change it comes from the lower 2 curves. They're both imaginary scenarios of we put the brakes on fossil fuel use at different rates, and we stop the growth of it, which would be the peak in the curves here, but we still continue putting the same amount in every year, making the problem worse, but we bring the use down, and if we do this reversal in direction by 2040, we still warm up by 3 degrees. If we bring it down a bit faster, the lower curve here, so that it turns over in 2016 or 2020, we should keep on the tortoise scenario to 2 degrees. Not very nice, but that's how fast we have to act to do it. Now, there's a third way to act, which I showed you before, which is literally start taking carbon out of the cycle that goes between air and plant and ocean and stays in circulation, but taking things out of that circulation, and if you do that, you will reduce the concentration in the air, which is what counts for both ocean and global warming. So here's one scenario, here's the other. I would finish by saying there are some reasons for optimism here, and I'll just list three. We have good longer-term power solutions for doing what coal and oil are currently doing for us. Even with current technology, things like deep geothermal and nuclear and so forth are capable of taking over the load if we do them fast enough. There will probably also be a third industrial revolution in the process of doing this, will give us even better ways of doing it. So there's that, and we can do the near-term part, this taking the growth out of the system by 2020, probably with nuclear and deep geothermal. The other optimistic point is we have indeed turned on a dime before. And I'll show you that as soon as I go through the three existing technologies. Plug-in hybrid vehicles that recharge at night off the electrical grid but give you enough for the complete commute, which is about 33 miles on average in the US, so that now you're taking the load off of using oil. Secondly, that you build enough nuclear and geothermal to retire a few of the old coal plants quickly. But finally, because all countries have a lot of coal and they're going to want to modernize, and if we don't want them to repeat all of our mistakes and undo all of our efforts, we need to subsidize them to use clean energy. And the easiest way I can conceive of doing this, I don't think we'll give them nuclear reactors, although 31 nations already have them. I think something like offering to drill deep geothermal wells for them and set them up in operation in exchange for a vow not to touch their coal, might be a way we could proceed with it. But it's got to be a global effort. It's not just us doing our part. We've got to think ahead for others as well. So that's one of the ways you get there, but here's the optimistic turn on a dime part. When World War II was looming, but we weren't in it yet, FDR put a lot of effort into getting industry ready to convert over to war production. And that was a little bit unpopular in many circles, and he had to pussyfoot around it quite a bit. But he did indeed set things up so that after Pearl Harbor, industry really did turn on a dime. That is to say, the automakers converted 1,000 automobile plants to war production and built 1,000 of each of two kinds of aircraft. And they designed, tested, built, and off the assembly line, the GM Duck, a truck that was converted to be amphibious, all in 90 days. Ford turned out one bomber every 63 minutes. I mean, this is the kind of, on the eve of a great war, you can do a lot of things that you would think would take decades. But we, certainly in the US, have a great deal of wherewithal to do this. So I just close with this quote from a few centuries ago. Edmund Burke, the Irish-English statesman, said, "The public interest requires doing today those things that men of intelligence and goodwill would wish 5 or 10 years hence had been done." Right time frame, too. Thank you.
So we have time for a few questions, so please approach one of the microphones if you have a question. So you won the race, so we'll start on the right, my right.
And terrific, thank you so much. The question is, just up until recently, our own administration denied there was a problem, and yet you're presenting years of evidence. There are scientists, they've said, oh, this is all hogwash. How can this be? And what are we missing today? Because, you know, we're still in that same mindset that they were saying this isn't really a problem.
Well, I mean, I suppose there are lots of answers to that question. Scientists don't speak directly to the people. I mean, that's to say, you know, we don't get particularly covered very often or well. That's part of it. Part of it is the he said, she said, you know, notion of doing news about science, where, you know, they call in anyone they can find to say the opposite thing and give them equal time. That's common in our media. I would add to that that the environmental reporters of the newspapers are a very sharp, well-informed bunch. I was with a group of them a couple of months ago at the NRC's nuclear reactor training facility, where they put on a few days of how we train our inspectors. And the questions those people were asking were 2 or 3 degrees more complicated than any story they could have gotten past their editor. So they knew a great deal more than they were actually able to report on. That's true certainly of the New York Times reporter, Matt Wald, but it was also true of the St. Petersburg Tribune. I mean, it was this whole group of about 20 astounded me by how well informed about the situation they were, but it wasn't getting out.
With regard to nuclear, you had it in one of your sidebars, cloning existing plants. I understand the French get one power plant model. It's kind of the Southwest Airlines model of producing nuclear power. What do you see as the political, scientific, regulatory chances of getting the U.S. to do that, one type of power plant over and over again?
Well, back about 97, the NRC changed its policy about reviewing in detail. I mean, so it didn't get to be a 5-year review for each power plant. They said that if you will stick to the standard model design, which is the one that's likely to be built in Texas next year, then you'll get expedited review as long as you don't change any detail. And you'll still have to have a site survey to show that it's environmentally sound to put it there and so forth. But furthermore, a nuclear plant can be built in just 2 or 3 years, construction time. So they can go much faster than they have gone in the past. I do despair about changing national policy with all the fears fast enough to do that. It's one of the reasons I'd prefer to go the deep geothermal route as fast as we can, because we don't have the fears of that, and it doesn't take mining either. Go ahead.
Would you please comment about corn-based ethanol and its effect on the consumption of natural resources, and also the results of
you're right. It's a bad
food
idea.
Supply.
I'll tell you another reason it's a bad idea than the ones you already know. If your transportation and your food come from sources that are simultaneously likely to be hit by a drought, you crash your economy a lot faster than if one continues and the other one goes down. Okay, I mean, you know, in a drought, if you could stop eating beef and eat the corn directly as bread or something and expand the supply of it 4-fold. But, I mean, if the commuters can't get to work and the economy, you know, shows it, it's just like planning, you know, your investment portfolio for old age. I mean, you want uncorrelated sources that when one goes up, the other one might be going down, but they don't both go up or down together. Same problem with this. You don't want to use a source like corn ethanol to do this.
I give a free lecture mostly for my own interest, based on Peter Ward's Scientific American, October '06. It's fairly accessible to a non-science audience because PBS did a 13-minute video called Extinction. and it's easy to present. I'm curious what you think of his process, the 9-step process where it starts with a pulse of carbon dioxide, ends with poisoning the atmosphere with hydrogen sulfide, and destroying the ozone layer, and evidently has happened repeatedly in our planet's history.
Well, there's lots of things worse that can happen than what we've been covering so far. And Peter, who's a colleague of mine, is painting a picture based upon what we know of, particularly what happened about 55 million years ago with the big greenhouse effect back then. And prospects for things like if you have methane burps, that you can get big fires lots of places very quickly. So there's a lot of other catastrophes that we're not covering here, but amongst the ones that we know are in store for us this century and which will produce a chaotic world for the kids, the students in college now basically have to face a world where the time they're 45 or 50, we could have a world where that's so unsafe and unpredictable that nobody will invest money to do anything.
One little addendum. You said not in store for us this century. It appears that this is likely at 6 degrees centigrade or Celsius increase. This is a possibility.
All the figures are Celsius, but I've been interpreting into Fahrenheit.
Okay. At 6 degrees Celsius. Anyway, the people out at UC Berkeley are saying we may hit 7.5 degrees by the end of this century.
The results you see are average scenarios of a spread that does indeed include that. That is to say, we don't know that the climate sensitivity is 3 degrees for doubling the CO2. That's just the average of ones that go from 1.5 up to 5.5 and so on. And which one nature actually uses, we haven't found out yet. We know from the way the ice caps have melted in previous ice ages, we can get a bit of a calibration. It does look like about 3 degrees, but that's not solved yet.
One of the first slides you showed was 50,000 years ago. What happened with the climate, and what was the connection with the human behavior relationship you had on that slide?
Yeah, basically climate was flipping back and forth on less than a decade timescales and then sticking in the new mode for a century or two and crashing back. So it's basically a very unsettled world, and people were forced to move around a great deal there. That's also the time of the out of Africa, may have been part of the movement. It wasn't doing anything different at 50,000 than it was doing at 30,000, and we don't know in the previous ice age whether things on this rapidity occurred because we don't have the time resolution in the cores that go back before about 120,000. So the thinking is that it's not any peculiarity of 50,000 years, which is really a 70 to 40,000 year span anyway. So, but what got me into this, in fact, was I was trying to figure out why human brains evolve so quickly, and climate fluctuations were just the natural thing to look at, because any evolutionary biologist will tell you that if you see speciation pick up and produce a lot of variance, the big climate change probably happened.
Sir, your lecture, very good from a technocrat point of view. But will the politicians of the world listen to you or do what you said? You said 4 fire alarms, we have to meet their requirements simultaneously. If we had, I know there was shortage of time, what do you think these politicians of the world will do? Anything or do nothing?
Yeah. Well, I mean, there's no lack of national politicians now that accept most of what the scientists are saying for the tortoise scenario, that many of them haven't heard of the hare jumpiness. There is that problem, but scientists don't speak to the people directly in this country with very much success. It has to be filtered through the media, through their clergymen, through other sources that they more traditionally get their facts and values from. And our immediate task, I think, is to persuade those leaders to take on part of the problem. And that's one of the reasons why the moral issues of you can't do this to other people. And this is really the developed world's doing it to the people on the front lines in the tropics that are going to get hit first. But if that kind of reasoning can prevail, we might really get somewhere with it much more quickly than scientists trying to systematically educate the population about what's basically a complicated problem involving things like feedbacks that people think they're about a suggestion box rather than a thermostat.
Dr. Calvin, you did not mention solar power or wind power or landfill gas as a generating fuel. What do you think those will show up in percentages for power generation in the future?
What was it? It was solar power, wind power. What was the third?
Landfill gas.
Landfill gas.
Right. Okay. Landfill gas is methane and CO2 bubbling up from landfills. And in Europe, they're going to pretty much stop this from happening with digesters for that actually produce power as well as capturing. There are a lot of opportunities with landfill projects to bury organic materials and take them out of circulation, just like the way they follow the ocean floor. I've just begun thinking about that. I don't know how big a project it would have to be to succeed. Similarly, trapping some of the soils that go down muddy rivers before they get out into the Mississippi, alluvial fan and turn into CO2. I mean, there are things, if you produce settling tanks to take that and then store it, that's other ways of getting into it. I mean, there's a lot of thinking that's gone into a few areas, but we're just beginning to think about how to do the others. I mean, if you talk to, I've been to 2 meetings this year with the ocean scientists that study the plankton part of this ocean acidification problem. And my overall experience from listening to them was to think that while very good work was being done, that not much had been done earlier. That they were in the beginnings of coping with the problem. Mm-hmm. Well, so that part it isn't encouraging, but it's a lot of very good work is being done now. The real problem is taking what we have now and convincing people to act on it.
Are you familiar with the use of the Barnett Shale to convert CO2 into methane?
The tar sands in Alberta is a classic example. I mean, there are ways to make use of marginal fossil fuel resources. And if you think coal is bad for putting CO2 in the atmosphere, they're worse.
Thank you very much. I know many of us have to get back to the fundamental mission of the university, which is, of course, evolving human brains rapidly. But I want to thank Dr. Calvin for an extraordinary talk this evening that has, I think, enlightened all of us, I think shed a great deal of light on what our collective mission needs to be. And I just want to thank you, at least on behalf of myself, if not everyone else here, for finding a bit of optimism to end the evening on. Please join me once more in thanking Dr. Calvin. It was really wonderful. Thank you so much. Thank you. It was really great.
This program is protected by copyright and may not be redistributed in whole or in part without the express written consent of Rice University Digital Media Services. This program is protected by copyright and may not be redistributed in whole or in part without the express written consent of Rice University Digital Media Services.